Now,
Okay.
that's to preempt any other prompts. All right, let's see, where did we stop? I think we covered Zener diode load line analysis, and then also load regulator analysis. Yeah, yeah, yeah. Zener diode regulator. Okay, diode clippers. So the two circuits that we're going to look at next is the clipper and clamper, collectively known as wave shaping circuits, because there are many circuits in electronics, or there are many applications in electronics where you would need to take a incoming signal, basically, which is a waveform, sinusoidal AC waveforms, or square or triangular, and we need to change or modify these signals. And so any circuit that modifies or changes the wave shape, we call them as wave shaping circuits. So there are plenty of circuits, but the two important ones that we look at is basically the clipper and the clamper. Clipper, as the name suggests, clips a certain portion of the incoming wave, okay? And clamping or clamper circuit clamps a particular waveform at a particular voltage level. So as the name suggests, clipping clips off a certain portion, and clamper basically clamps the waveform at a certain level. So this is a basic clipper circuit. We have diodes going in both directions. So this can act as a clipping waveform, clipping wave shaping circuit for both the positive as well as the negative peak. Now, most of the electronic circuits that you look at, you should only worry about analyzing from the terminals. So terminal characteristics. So the properties, the semiconductor properties of these diodes and transistors and the other circuits that other devices that we'll look at, those are introduced to students so that they can understand the concepts and everything. But when it comes to circuit operation, you should worry about understanding the terminal characteristics, meaning how does the device behave at its terminals, okay? And that is going to be very important when we analyze circuits like these. So in a clipper, we know that if you use a diode in a clipper circuit, if the diode anode is at a higher level than the cathode, the diode is forward bias, behaves like a short circuit. On the other hand, if the cathode is higher, then the diode is reverse bias and the diode is off, so it behaves like an open circuit. And those are the properties that we'll use to analyze this circuit, right? So yeah, so if diode is on, it's a short circuit. If diode is off, then it's an open circuit. Oh, open circuit. So SC and OC, basically short circuit, open circuit, replaced with a wire and basically replaced open. Now that's basically, again, from the ideal diode model, right? So let's just take a look at the positive peak here, okay? You have a waveform, sinusoidal waveform that is being applied. Peak value is 15. Vm or Vp is 15, meaning it swings between plus 15 and minus 15, right? So negative peak is at minus 15, positive peak is at plus 15 volts. If you look at the diode clipper circuit, ignore this branch for now. Just focus on this branch. What do we have? We have a diode anode that is connected to the positive terminal right here, connected to the 2 kilo ohm resistor. V out has a positive reference up top, okay? So when the incoming waveform goes to its positive peak, what happens? The cathode is held at 6 volts, right? So the incoming waveform, as long as V in is less than 6 volts, what happens to the diode? Cathode is at 6. If the incoming waveform is less than 6, what happens? It's reverse bias. Diode is off. So if the diode is off, your circuit is like this. And again, we are only analyzing one peak at a time, right? The diode is off. What do we get at the output? We get this waveform at the output, right? All the way to 6 volts, meaning the input signal is allowed to reach the output unimpeded. So the input signal, which is climbing from 0 to 6, reaches the output with no problem. Once it crosses 6 volts, ideal diode conditions, we would just say 6.01, fraction above 6. Diode turns on. When the diode turns on, replaced with a short circuit, and now, so in V in is greater than 6 volts, D is on, replaced with a short circuit. Exactly. And then you have plus minus 6 volts connected directly to the output. It doesn't matter what the input is doing, because the property of a voltage source is to supply its rated voltage at its output terminals, no matter what is connected. EE201, chapter 1. Voltage source will always supply constant voltage at the output. So V out goes to 6 volts. So if you look at the entire waveform, V out, so this goes to 6, stays at 6. Doesn't matter what the input keeps doing, right? Input AC signal could go above 6, doesn't really matter. Output only sees this battery as 6 volts. That's it. Until V in goes below 6, which happens on the other side, or the downside of the waveform. The downside of the waveform, once it goes below 6, we go back to scenario number 1, where the diode goes off, the battery is disconnected, and you only get this again. So the only portions where the diode is actually, the input signal is reaching the output is basically these portions right there. These two portions of the input signal are the only ones that are reaching the output. The middle portion of the output is basically the 6-volt battery. Does that make sense to everyone? Yes. Not yet. Not yet. Not yet. Any questions about this operation? This makes sense, right? Okay. So at the same time, if we do look at B, what happens? At the same time, when the positive half cycle, if we do look at B, cathode of B is held at 9 volts. Anode is going to be at positive. It's going to be, what is it going to be? It's going to be reverse bias. It's going to be off. Does that make sense? So diode B is always going to be reverse bias, because the negative end of the supply, if this is positive, then the negative end is being applied to the anode. So it doesn't matter what value the positive waveform takes, it's always going to be reverse bias. Okay, so diode B basically does not interfere with operation of the positive half cycle. Does that make sense? Now, this operation applies exactly to diode B when we go to the negative half cycle. So the negative half cycle, in the negative half cycle, diode B, again, the cathode is held at plus 9 volts. Diode B will remain off until the negative peak now goes above 9. All right, so when the negative peak comes, this becomes plus, this becomes minus. When it crosses 9 volts, diode turns on, the 9-volt battery gets connected to the output, and we have a flat output line. So these are being supplied by the 9-volt battery. This is being supplied by the 6-volt battery. And of course, with reference to V out, the battery is minus up top and plus at the bottom. So V out is seeing minus 9 volts. Does that make sense? Right? Value is still 9 volts, but V out reference is positive with the negative end of the battery. So it's minus 9 volts. So again, to recap, the flat line clipping portion value comes from the batteries. The diodes are only conducting on either side. Sorry, diodes are not conducting on either side. When the diodes are conducting, the output goes directly to the battery. And that's how it works as a clipping or a clipper circuit. Yes. Yes. So V out is measured here. So if you imagine a digital multimeter, you're putting the positive reference here and negative here. And the battery has a negative terminal up top. So it sees minus 9 volts. But the operation in both cycles is exactly the same. Positive half cycle, it's diode A. Negative half cycle, it's diode B. And it clips. If you remove the battery, if the battery goes away, and these diodes are real diodes, what do you get? If you remove the batteries, meaning there is no battery whatsoever, negative half cycle, it's diode. Let me finish writing this. Turns on and V in crosses 9 volt. Okay, so now the scenario is no batteries and real diodes where VD is 0.7 volts. So VD is 0.7 volts. What happens? How does the operation change? Think on it for 10 seconds. We have an input waveform being connected. Positive half cycle, the positive will affect diode A, negative half cycle will affect diode B. As long as the input is below 0.7, what happens to the diodes? Diodes will be off. Output is equal to whatever the input is. As soon as the input V in crosses 0.7 volts, diode turns on, becomes a short circuit. So the diode is a short circuit. What is V out? V out is equal to 0 volts. And the same thing will happen when it's the negative half cycle. So the output of just 2 diodes with nothing will simply be like this. That's it. This would be plus 0.7. This would be minus 0.7. Everything else will be clipped. Does that make sense? So that's why we introduce a battery depending on how much we want to clip. Okay, questions? Was clipping circuit a part of the lab? Anyone? We didn't have clipping circuits. Okay. Okay. Yes. You tell me. Where can you all think of an application? So the question being asked is, where do we actually need clipping circuits? So Well, no, compression would be different, but clipping would be a little different. But this is an application pretty much everyone has used. Where? Increasing the, oh, the fan, that was the transformer example. Yeah, but not like a clipper. I think I've mentioned this before. Power surge protectors. Say, imagine you're using electronics and there's a power surge, or there's thunderstorm and lightning, and they would say usually do not use anything while a thunderstorm, or especially when lightning is present. The reason is because lightning can strike buildings. It'll introduce like a huge current or power surge in your power lines and blow out your expensive electronic equipment. So power surge protector usually will have a clipper. So it doesn't matter, what comes in. If it's above a certain level, it's going to get cut off. That's an example where everyone has actually used it in real life. Clamper circuit, it's not as common like a real life example, but again, clipping, as I said, it's a common example. Like power surge protectors, very common. But what is the obvious disadvantage of this kind of circuit? Yeah, you need a battery. Batteries need to be charged or replaced every so often, so it's not very practical. And that's where we use this kind of circuits. Much simpler, just two diodes and that's it. Two diodes and that's it, back to back. Because Zener diodes operate in reverse bias, right? So they're going to be off until it reaches a certain level in the reverse direction, right? So you take out the batteries and simply insert a Zener for that rated voltage, and that's it, done. So in this example, this is actually an exercise in the book. The diodes are real diodes, so it's like 0.7. 0.7 VD is required to turn on the diodes. So if you just take a look at the left branch, so circuit A, let's just look at this. We got this diode, and we have a 9.4 volt Zener. Right? 9.4 volt Zener. So what happens? In the positive half cycle, this requires 0.7 volts to turn on. Everybody finishes writing. Yeah, question? No, I was just saying I'll wait because students were drawing, so I'll wait to speak. Anyone want to take a gander at this on how it works? Why don't y'all think on it for a few seconds? Well, for at least a minute or two, not just a second. Think about what we just saw in the previous circuit. You have the battery. Battery was connected. Here, let me go back. Battery was connected plus at the cathode and minus at the other end. So Zener diode works in reverse bias, right? Forward bias is just going to work as a normal diode. So what happens? In the positive half cycle, is the Zener diode connected in reverse bias? Yes, it's reverse bias. So we are working in quadrant 3. So what I'm trying to get at is like how to train your brains to analyze a circuit. All right, that's why I'm not like just going and giving you the answer, because once we get like BJTs and op amps and stuff, it's going to get, you know, a little faster and harder. So at the beginning, I want you all to train your brains. So positive half cycle, Zener diode is reverse bias. We established that. Diode D1 will be forward bias. It requires 0.7 volts to conduct. However, if the voltage, this is a 9.4 volt Zener. I think maybe the example uses 0.6 volts instead of 0.7 to round it up to even 10. 9.4 and 0.6, what happens? Yeah, positive voltage. Diode D1 turns on. Does it turn on? Zener is going to prevent it from being turned on. Effectively, it is performing the same action that the battery did. Zener, quadrant 3, what happens? The reverse bias. Zener stays off until it reaches 9.4. And the Zener diode remains off, so it doesn't matter what happens here. This cathode, this end has to exceed this voltage plus this voltage. So when it crosses 10 volts, it overcomes this plus this 9.4, meaning it turns both of them on. Does that make sense? Think on it for 10 seconds. It is doing the exact same thing that the battery did, but now the V out is not connected to a battery. It's connected directly to the input, V in signal. And so 0.6 plus 9.4 stays flat until, and so it clips it at, as Baxter just mentioned, 10 volts. Think on it and see if that makes sense. Yes. Yeah, it's still clipping. So let's say we apply 15 volt signal here. You know, it starts climbing. Now, if the Zener was not connected, D1 would just turn on after like 0.6 volts, and then it would just be 0.6 flat. But because the Zener is connected, it's still off. So if this is still off, whatever input we give is available at the output. So input is here, 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 it still reaches the output. And as soon as it crosses 10 volts, diode D1. So D1 and D2 both turn on. And when they both turn on, behaves like a short circuit. Zener regulator, remember, once it turns on, it keeps the output voltage constant by driving all of the current through it. So even if the input is increasing, the current through the Zener will increase, but the current that is going to the output is not. So the output remains constant. Remember from last class, Zener regulator, current through the Zener will increase, but the current through the output will not. And so the output voltage will remain constant, which is basically this 10 volt line. And then again, when it drops below 10, cut off, we have a clipping circuit. All right, questions? Is anyone being inspired to create their own surge protector? You can do it as a project or something. What's your shirt? Oh yeah, that's right. I have potential. All right, questions? Any questions at all? Okay. So what happens in the other branch? Other branch right here. Yeah, so yeah, so we have D3, D4, D5, and all of them are 0.6. So diodes, the normal diodes, I should have pointed out at the beginning, diode VD is 0.6 volts. So what happens in the negative half cycle? So to analyze the circuit, look at whether diodes are connected. If the anode is connected to this end, so positive half cycle, the diodes are reverse bias. Diodes are off, nothing happens. This branch doesn't affect positive half cycle. Negative half cycle, this goes off because the anode is connected here, but these turn on. And each of these requires 0.6 volts. 0.6, 0.6, yes, Sam. Yes, per diode, yes. So you just sum them up. Good question. So you got 3 diodes back to back to back. How much voltage do we need? 1.8. So this is not to scale, of course, but 1.8. So at minus 1.8, it clips. 137. Okay. How about here? You got 4.4 plus, as the mentioned. So you have to keep that in mind. Zener diode is still a regular diode in forward bias, right? So if you have back-to-back Zeners, you got 4.4 in the reverse direction plus 0.6 in the forward. So each half cycle, in each half cycle, one diode will be reversed, the other diode will be forward bias. So in the positive half cycle, D6 is anode is connected up here. So it's on 0.6. This will be reversed of 4.4. In the negative half cycle, D7 is forward bias, D6 is off. Again, 5 volts. So clipping 5 and minus 5. So each diode forward bias will require 0.6 volts. Yes. We always have to the 0.6. Well, it'll be given in the statement, either ideal diode or how much it's required. So in this case, VD is given as 0.6 to turn on the diode in the forward bias. Yes. 1 kilo ohm resistor will also have a voltage drop. Yes. So if you take VO and you connect it here, then you have to calculate what the current would be and then determine it from there. Yeah. Yeah. Okay. That was fun exercise, but let's move on. It's what? It's close to 140. Let me move on to Clamper because I want to introduce BJTs today. Bipolar junction transistor, that is BJT. Okay, Clamper circuit, not as common as Clippers, but again, do a quick brief overview of what a Clamper circuit is and how it works. Basically, it uses the charging and discharging capabilities of a capacitor. Okay, capacitors, like in capacitors and inductors, can store energy, right? It can store voltage. So when a capacitor charges up, it can store that voltage for an infinite amount of time. Real life capacitors will start discharging. If the capacitance is very large, what happens to the discharge and the charging speed? Takes longer. Mathematical equation, anybody remember? Yeah. It's not, yep. Tau is equal to RC, time constant for a RC circuit. Anyone remember it for the inductor? Yeah, asking me or telling me. Is it? Yeah, anyway, coming back to our circuit. Capacitor right here connected to a diode circuit in conjunction with a battery. Positive half cycle, what happens? Diode gets forward bias, capacitor charges up, circuit current is actually flowing in this direction. Actually, when I say this and that, let me make annotations here. So we have a battery here, minus and plus. Cathode is held at minus 5 volts. So the input needs to go above 5 for it to actually turn on. When it does that, current flows in the circuit in this direction. Capacitor charges up to plus 5 volts. Okay, capacitor charges to plus 5 volts. So VC is plus 5 volts. Then in the negative half cycle, what happens? We have the battery that prevents the diode from turning on. In the negative half cycle, this 5 volts with the capacitor is added. So V out goes to VC plus V in. Okay, so this capacitor voltage is going to discharge at a very, very slow rate because of the very low time constant. And so that capacitive charge introduces a DC component in the waveform. Okay, and so it clamps the positive peak of the input waveform to minus 5 volts. It's a little complicated circuit. Even EE majors students have a little bit of trouble with this. So it's I like to do the clamping circuit, but again, we won't do like any in-depth analysis. So, but that's how essentially it would work, a clamping circuit. Okay. If we wanted to do a positive clamper, then we simply reverse the diode and the battery direction. And so it will turn on, the capacitor will charge the other way around, shift the peak up. So the negative peak is now clipped at a different level. You can also change the battery levels, battery terminal. And when switching the battery terminal, you can shift the waveform, well, wherever you actually want it to go. But again, it's, you know, see lots of confused faces. I see some nods. Okay. Takeaway is, in one cycle, the capacitor charges. In the other cycle, the capacitor stored voltage is providing a DC level to that same waveform. Okay, that's what's happening. The value of the capacitance has to be sufficiently large so that it remains constant with respect to the incoming input waveform. So the incoming waveform is AC. The frequency is going to be very, very high. So since the frequency is high, the capacitor cannot discharge as quickly. And that's the key to that operation. All right. 1:45, still have a few minutes left. Sorry. 2 announcements I wanted to make. Homework for Zener. I was going to make it available last night, but I wanted to make some changes. There's only going to be like 2 or 3 problems, not a lot. 1 tutorial, and then quiz on Monday based on whatever we have learned in the past week. Okay. So quizzes every Monday, always based on the material that we learned in the previous week. All right. And I'll make sure that the homework from now onwards will be assigned at least on Wednesday, so you can get started in an early start on your homework. Secondly, I know some of you have labs on Mondays. Does anyone have a 361 lab on a Monday? Tuesday. So nobody has it on Monday, but somebody has it on Tuesday, right? And all of your pre-labs are due on the day of the lab itself. Okay. So what I'm going to do is I do this for 250. Started doing it for 251. I also do it for 361. Is I'll record a short video on how to solve the pre-lab, and I'll post it over the weekend, so students can take a look and try and get it done. Yes. Yeah. So I started doing it for 251. Lots of students said they appreciated that, so I'll do it for 361 also. I'm not teaching 361, so I have to be in communication with the other professors to see what is going on. But the earliest lab is on Tuesday. I'll try to get it done by at least Sunday night so that students can have it for solving the pre-lab. Okay, those are the two announcements I wanted to make. And chapter 2, bipolar junction transistors, the most, yes, yeah, PDF, right? Yeah, PDF is available. So I know the name sounds kind of sinister, but there's a reason for bipolar. The reason is, remember majority and minority carriers? Remember I talked about majority and minority carriers? So the current flow in this device occurs due to both minority as well as majority carriers. Okay, and that's why it's called bipolar. Okay, bipolar junction, and there's junctions in there. So bipolar junction transistor, BJT. Okay, does anyone know when the transistor was invented? Well, no, that when it actually wasn't Silicon Valley. It was 1947. It was 1947 in Bell Labs. Okay, Bell Labs, December 16, 1947. Three people in the team: William Shockley, John Bardeen, and Walter Bertain. I try to recap try to remember the history, but I again forget. One of them, I can't remember which one. Was it Bertain or was it Shockley? Or they had a big falling out. So the Nobel Committee actually wanted to give them the Nobel Prize for this, but it would be shared, and that guy said no. He was that mad or something. I don't know what it was. I'll have to. It's been a while since I reread that history, but I need to reread the history. Anyway, this was in Bell Labs in December 16, 1947, long time ago. This is the basis of all modern electronic devices. Okay, before the invention of this solid state, well, this wasn't even like completely solid state. It was a germanium semiconductor. But before the invention of this, everything was run by vacuum tubes. Vacuum tubes are big, they are hot, requires a lot of energy, requires a lot of room and space, and highly inefficient. But that was, this was the world before we had anything like this. So it was still the best option. So everywhere, all electronic circuits, devices, they use vacuum tubes. They came up with this. This was known as the point contact transistor. The name transistor comes from the fact that it transfers, well, it's sort of transferring the resistance from one junction or one end to the other. Okay. Now, of course, this was an important milestone in electronics, in the field of electronics. Basically, after this came into effect, lots of people started doing research, coming up with their own devices and everything, and then microprocessors and integrated circuits soon followed after that. Okay, so I just like to give this little bit of history lesson. This was a point contact transistor. It was simply a plastic triangle on a germanium plate on a germanium semiconductor, which was sitting on top of a metal plate, making contact with it, right? And right at the tip of this transistor, there was a gold pad, gold contact, a small opening in that gold contact, which allowed the current to pass through into the germanium semiconductor. Yes. Well, actually, let's see if we can spot something over here, but not really. I actually knew the answer probably about 10 years ago. I'll have to refresh my own memory, but that's a good question. It's a good question on how small it actually was. I should probably include it in my slide next time. So what was I saying? Oh, there's a gap in that gold contact at the tip of the triangle, which allowed the current to actually go through. Germanium, of course, is a semiconductor, And so when you had a small electric current passing through, it came out on the other side amplified, or like basically large in large in amplitude or magnitude. So it works as an amplifier, which is one of the most important applications of a BJT. So you can use a BJT as either a switch or an amplifier, depending on the mode of operation. Okay, so the first experimentation with this was as an amplifier. That's what they used vacuum tubes for at the time, like vacuum triodes and stuff. That's what they used it for, to amplify. But, those were like vacuum tubes. We are working in the field of solid state devices. So solid state devices basically are using semiconductors. So they are made up of two PN junctions connected back to back. Okay, they're connected back to back, and there are two PN junctions. Okay, two PN junctions, meaning there are 3 layers. And depending on the configuration of those layers, you have a PNP or a NPN transistor. Okay, PNP or an NPN transistor. Symbol for a transistor or a BJT is given right here. Circuit symbols. More often than not, this is not typical. We would not have this kind of circle in there. This is far more typical. Also, most of the common transistors in use are NPN. So mostly we would use NPN transistors, not PNP. There are 3 terminals connecting to all 3 of those layers. Each terminal has a specific function and has a specific name. The middle one is known as the base. One end is known as the emitter because it emits the carriers, it emits the electrons, and then the other end is the collector. And we look at a little bit of semiconductor physics or semiconductor operation of the device, and then we'll move into circuits. Now, this is taking a step ahead, but you see the angle in the symbol, right? And you see an arrow. If the arrow is coming out, it's a NPN transistor. If the arrow is going in, it is a PNP. The BJT is usually or typically drawn like this. There is another transistor that is drawn with flat horizontal and vertical lines. Anyone know? So FETs, field effect transistors. But again, we'll take a look at that later. Okay, so this is an actual slice of a BJT. If you have your lab kits, it's a your lab kits will have a small black epoxy, something like this. And you'll have 3 leads coming out. And so it'll say 2N something something, 2N 2222. And this is a slice of that device. Okay. Anyone remember the number of the diodes that they use? The model number? 1N4000 something. That's a 1N4000 series. Transistors is 2N 2000 something. What does 1N and 2N stand for? Well, not just N type, it's just the number of junctions. So 1N stands for diode, 2N stands for BJTs. Okay, 2 junctions. So let's take a closer view of that. So that entire package that you see is just packaging material. That's not the transistor. Transistor is like right here. That's it. The transistor is actually right there. Yes. This is kind of like epoxy packaging material, hermetically sealed. So you can't like really open it up without damaging it. I mean, there's no opening it up. You just have to, cut it up, slice it up. This is aluminum contact. This is actually silicon, and that is gold. So gold wire bonding that takes the connection out. Yeah, so basically you have these big leads. So this leads that you see here, 3 ones, that's what this is. So this one is probably like aluminum, I guess. Most likely it's just aluminum. Maybe coated with, well, I want to say chrome, but probably not. Some sort of metal mixture, I would say. And then it goes inside the package, and this wire bond actually makes connection to that big leads. Okay, so we live in that microscopic world, if you will. So that's the close-up. That's the actual silicon die. That's a gold bond wire that's making connection to the emitter in there. That's just the epoxy. That's the aluminum collector contact at the base on the back side of the device. Okay. Now, if you take the clean room class, BMET 435 or EE 473, only offered once a year, we actually make diodes. We actually do processing like this to create diodes in the clean room fab. Yes. Well, the current is very, very small. Very, very tiny, very, very small. Yeah, good question. Yeah. Most electronic devices that we work with, first it was like 5 volts. Now it's like 3.3 volts, and it's very, very small. So the voltage, the currents and the voltages that they work with are it's very, very small. This is, well, not quite 30,000, but it's like looking from the top under a microscope. Okay. So here's a transistor, here's a transistor, and the 3 elements, emitter is right here in the middle, base is kind of like around it, and then the collector is basically all the way underneath. Okay. It's a little hard to visualize, but if you look at it from the side, this is what it's supposed to look like. You have a silicon wafer, and then you introduce dopant impurities in there. So the way diodes are made is basically you have a silicon wafer, let's say a P-type material. Then you open up a small opening from the top, and you insert N-type material from the top. When you insert N-type material, what do you have inside the wafer? You have N and you have P. You got a PN junction. And so transistor, you first, like this one is an NPN, so you got an N-type silicon wafer. You open up a hole in there, opening, and then you insert P-type material. Once the P-type material goes in there, you have one PN junction. Now you open up a second hole, smaller hole, inside the big one, and you insert another N-type material from the top. And that's why the base is kind of encapsulating the emitter, and the collector is encapsulating everything. Does that make sense? So the image that we viewed earlier, which is right here, you see this is a complete transistor on the left and the right. But you had the collector, which is the entire work surface, if you will. Your entire work surface is the collector. You insert the base, and then you insert the emitter inside the base. And so again, we actually have a clean room fabrication facility at Cal Poly, which not many undergraduate universities do. And there is a class that is offered every winter, in case anyone is interested. So solid state BJT, we have, we're run out of time. Okay, all right, we'll stop here and then pick up here again on Monday. Again, reminder quiz. So my agenda for getting back to my office is first to post the lecture video, then make the homework available, and then I'll post information about the quiz. And then again, if any students want to come talk to me about anything, I'll be in my office. I'll be available over the weekend also if you need help with the homework. Sunday night. Again, just a couple of problems, not more. Mostly Zener diodes, yes. All right, have a good weekend, and I will see you all on Monday.